Alright, so today I'm going to be showing you guys a pretty quick proof for the size of the power set being 2 to the power of n using combinatorics and the binomial theorem. So before I get started on the actual proof, I think it's important to look back at what a power set actually is and kind of the process of how you build it, because that's going to be pretty important for the proof I'm about to show you guys. So we're going to start off with an example. We're going to call this example, or we'll say A is equal to the set containing the elements 1, 2, and 3. So we know the size of A is equal to 3. And we also know that the size of the power set of A is going to be 2 to the power of the size of A, which is equal to 8. And just to show you guys that this is true, we're going to actually take the power set of A. So we're going to start with the empty set, because the empty set is the subset of every set. And then we're going to pick out the singleton sets of 1, 2, and 3. And then subsets of size 2, so it's going to be 1, 2. We'll do 2, 3, and then 1, 3. And then finally, the set itself, and we'll close these brackets. So, if you notice, we have 1, 2, 3, 4, 5, 6, 7, 8 elements in the power set of A. So, that's neat, but as you all hopefully know, you can't prove absolutely a proposition with an example. So we're going to say our proposition is that, how should I word this? We'll say if A is a set and n is the size of A, and some of you might notice how I'm avoiding the use of the word cardinality, because to be completely honest, I don't know the rigorous definition of cardinality, so I don't want to, spread any disinformation or anything like that, so I'm just going to stick to using size. If A is a set and n is the size of A, then 2 to the power of n is the size of P of A, or the power set of A. So, if you notice, this is a pretty simple proof format. It's just the direct proof, if A then B. So, to start our proof off, let's look at the process we kind of followed here with taking out all these subsets of A. So to begin with, we looked at A and we said we want nothing. And that's what represents the empty set. So we're going to start this off with, firstly, begin by choosing subsets of A of size 0, which is simply the empty set. And then, after we picked the empty set, then we looked at all subsets of size 1, and we got these singleton subsets. We have the set of 1, the set of 2, or the set containing 1, the set containing 2, and the set containing 3. Next, choose subsets of size 1. And we do that with subsets of size 2, and subsets of size 3. And notice this process stops once we pick the actual set itself. So, let me think of how to write this. We could say we can represent choosing subsets of size k as such, and choose k, which hopefully you're all familiar with that. That's just basically equal to, if you had a set of size n, you're basically looking at the number of subsets of size k that you could pick from n. So this is going to be some value here. It's equal to some factorial, but that's not particularly relevant for this proof right now. And honestly, I don't even remember what that is, so we're just going to not do that. So we'll say, so we have n choose 0, n choose 1, n choose 2, and if you noticed, we stopped here at n choose n, because if our k value here is greater than n, that's absurd. You can't have a subset of a set where that subset is bigger than that set. And I think hopefully that's self-explanatory. So we have our, I guess, list of combinations, I suppose. So what we're going to do next is then adding up this list should give us the number of subsets of A. Also, this is probably not going to be that good of a proof, but as long as you have the idea, I'm sure a lot of you watching are way better at writing proofs than me. As long as you know the idea, you can make this look real pretty. Then adding up this list should give us a number of subsets of A. So we have n choose 0 plus n choose 1 plus n choose 2, and so on until we have n choose n. Now, this is a series. It is very easy to squish a series together into summation notation. So that's exactly what we're going to do. We're going to say this series is equal to the sum of n, k starts at 0, of n choose k. Now, hopefully, you guys are familiar with the binomial theorem, and I'm just going to write it out up here. So, it's essentially this: n choose k of x to the power of n minus k of y to the power of k is equal to x plus y to the power of n. So, if you notice here, we have this first part, and we're missing this second part. So, we're going to be sneaky. What we're going to do is we're going to rewrite this guy as, thinking of how to word this. I'll just say, rewriting our sum. We have n, k equals 0. If n choose k of 1 to the power of n minus k times 1 to the power of k. And this is perfectly okay, because 1 to the power of anything is always going to be 1. This one times this one's going to result in 1, and this times 1 is just going to be this. So these two statements are completely equivalent. But looking at our little rule for the binomial theorem over here, our equality, we can grab our 1's here and take the quantity of 1 plus 1 to the power of n, add like terms, and we have 2 to the power of n. And that wraps up our proof. Draw our little nice shaded in square, and that's it. Thanks for watching.